And back to our lifting problem. So let's jump past everything we did before. Oh, there we go. And now we get to our problem. And this is where I left you last time. Okay. So we got old dude hanging out up here, huh? There's old dude. He's picking up a chain. He's got to pull it up. It's a 10-meter chain. But he's 11 meters above the ground. Now, we have some choices here. You see how dude's 11, did I say feet? Meters. Sorry. I am American, so I use feet. I always want to say it when I'm thinking about lengths. But it's 11 meters above the ground. But the chain is only 10 meters long. So it doesn't actually touch the ground. So on our setup, we're going to have some options. Well, we know our formula is the work is equal to, and I'm going to write it a little differently. Rho times gravity. Those are constants. Those are merely constants. And now we want to think about how long is the chain. The chain is 10 meters long, so we subtract out our y. That's saying for any given height that it's already sitting at, maybe we went from 10 to 5, the difference between 10 and 5 is 5. So that's what we have left. This part is what is left to pick up. And we know that when you're lifting up the chain, the mass of the chain is different as you put more and more up on top of that scaffold. So the weight is going to vary. Did I say weight? Sure, let's use the term weight. Now, we have choices as to how we want to do this. We have choices. We could say that this goes from 1 to 11, right? Starting at 1 foot or 1 meter. And then we're going all the way up to 11 meters. So we can do that if you want. Or we can make our life a hell of a lot easier. Do you like plugging in ones at the end, or do you like plugging in zeros? It doesn't matter that it's starting at 1 and going up to 11. We choose. We choose where we make our x and our y axis. And on this problem, the example gives you where it's like, hey, make your x-intercept start up at or the x-axis start up at 1 meter. So you're like, get rid of this nonsense. It's 10. It's from 0 to 10. Let's go. Let's go. Do we have our whole thing in there? Yeah, we do. We're good to go. Now, oh, shoot. Wait a second. We know rho. Rho is equal to 1.5 kilograms per meter. So we could change that out. I'll do that later. These are just constants. They're just constants. I'll do it at the end. Because in your homework, you're probably going to have to write rounded decimals. On tests, shoot, you're just going to leave that crap sitting there. So let us go through and leave these constants over here. We'll take an antiderivative on 10. We're going to get 10y. And then we're going to get minus y squared. Oh yeah, over 2, evaluated from 0 to 10. See how much simpler it is to deal with a 10 and a 0 than a 1 and an 11? Absolutely. So we have our two constants at the outside. So we have 10 times 10 minus 10 squared over 2. And then we subtract out our 0 because 0 is freaking rock. And what do we got? We got rho times g. Was that 100 minus 100 divided by 2? 50. So we have 50 times rho times g. And I would now replace it with 50 times 1.5 times g. And 50 times 1.5, that's 75 times the force of gravity, joules. This is how we'll answer on an exam. I don't want you putting in 9.8 or 9.81 and you won't have a calculator. However, in your homework, you may need to punch this thing into a calculator and go, ooh, it's 75 times 9.8. And why am I writing it as positive 9.8, not negative 9.8? Well, it's because the gravity is pulling, I shouldn't use the word pull, but it's pulling down. We're fighting against it, all the work. So this turns out to be 735 joules, approximately, right? Because the force of gravity is not 9.8 meters per second squared. It's not 9.81 meters per second squared, but it's about that. So that's how you would punch this into a calculator. Cool. Let's make note of this, because there's a part B to this problem as well. All right, now, same scenario. Dude's 11 meters above the ground, got a 10-meter chain, but now got a bucket that's 1 meter high. So now when we're looking at this thing, there's the chain, but then the bucket's on the ground. Oh, so now we actually have something that's 11 meters long. Cool. Is attached to the chain and rests on the ground. If the mass of the bucket is 15 kilograms, how much work is required to lift the bucket to the platform? Okay. Cool. This isn't bad. And if you hit a help me solve it, it's going to show you in a different manner. But the way I would do this is like, whoa, hold up. I already know the work. I already know the work it took to mull up the chain. That was 735 joules approximately, right? Now I just need to know, how much work does it take to move the bucket all the way up? You know, how much does it take to move the bucket all the way to the top? So as you're lifting the bucket, does it change its mass? Does the bucket change its mass? No, it doesn't. It's still a 15 kilogram bucket. We don't need calculus for the bucket. We needed calculus for the chain because the chain would vary in its mass as we're lifting it up. But the bucket is the bucket is the bucket. So what was our formula again? How did we do this? I swear it's up at the top. Oh, there it is. Work is just force times distance. The mass times gravity times the distance it needs to travel. So to move just the bucket, like over here, this was for the chain. So to move the bucket, we're going to say, well, it weighs 15 kilograms times the force of gravity that it has to overcome times the length it needs to travel. Well, since it started at 0 and needs to go up to 11, we multiply by 11. I'm going to grab a calculator out because there's a decimal in this. I'll actually probably get an exact value. I don't know. Let's find out. 15 times 9.8 times 11. Hey, look at that. That turned out to be 1,617 joules. 1,617 joules. So the total work is going to be 735 plus 1617 for a grand total of 2,352 joules. And that would be our solution. I like these problems. They're not too bad. Trust me, they're going to be a lot simpler than when we start messing around with pumping problems, taking water or something out of a glass or an inverted cone. But get this process down. I won't use any other tricks with you. They're all pretty much the same thing. And remembering this, if you lift a chain or a rope or anything like that, as you lift it, there's less to pick up. Why it varies, why we need calculus. To move a bucket up, we don't need calculus. It still weighs whatever it weighs. Again, I shouldn't use the word weighs. But yeah, that's our game. Do you get it? I hope so. Because, again, I like these problems. You can take those words for whatever you think they mean. But I like these problems. Hint, 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 hint.